Hi guys! This is the second part of the three-part lecture on the topic area of a plane region and arc length. Now in the last video, we learned that if I have two curves, let's say y equal to f of x and y equal to g of x, we can try to find the area between these two curves, bounded by the vertical lines x equal to a and x equal to b, by just finding out the integral of h dx, where h is just the difference between f of x and g of x. Now, this type of definite integral is called a definite integral in terms of the variable x. For a reason, because every part of the integral is in the variable x. From the dx, the h, which we have learned to be just a change in y, are both functions of x, and the limits a, b are also values of x. We can also call this a definite integral using vertical rectangles because the way we analyze this is to make vertical rectangles with width smaller along the x-axis. Now this type of technique is a very good technique in finding general areas of plane regions. However, sometimes this technique will become tedious and cumbersome when you apply it on different types of areas. In this video, we are going to be dealing with an alternative solution for this that will help us evaluate and set up some regions, especially those that are governed by another variable, in this case, y. For that, let's have the following example. Let's have this parabola facing to the left, given by this parabola here, and a line slanting to the right. We will see here that if we wish to find the area of this region, well, one, we need to split this along this line, primarily because when you try to trace from the leftmost x point, the upper function will change at this point here and then will continue along the parabola here. Another big difficulty for this example is finding the functions of x, primarily because the expression of this parabola is a quadratic expression in the variable y. That will give me x values that have square roots, which will be a little more difficult than the usual polynomials that we have discovered. One way to think about this is that instead of analyzing this vertically, we are going to analyze it horizontally. When you do a horizontal analysis for this, you will see that the height of the rectangle now will be contributed by the right function here, or right curve, and the left curve here. Unlike this case where the top function changed, in this case, the right function will remain the same and the left function will also remain the same wherever I draw a rectangle in my region. This type of analysis is similar to what we have before, but a counterpart to the vertical rectangle case. Instead, we're going to be analyzing this using a horizontal rectangle. Now, what is this horizontal rectangle? As we have discussed in the first video, whenever you have a horizontal rectangle, the height is a change in x. And that means it's the x-coordinate of the right curve minus the x-coordinate of the left curve. And because whenever you are going to use the horizontal rectangle, the width is in terms of y. So if you're going to be using the variable y, the height will be a change in the x-coordinate, just like we have seen here. And that will mean that when you isolate x in, for example, the right curve to be x equal to v of y, and the isolation of x in the left curve is x is equal to u of y, then that will mean that h is just v of y minus u of y. You will see here that if you're going to analyze it on a horizontal rectangle, there's a change in how you compute for h. Also, the variable that we use is a little bit different as well, not in terms of x, but now in terms of y. But the concept that we have is very similar to the introduction that we had in the previous video, and that is, if in the vertical rectangle, the height is just a top minus a bottom, for a horizontal rectangle, the height is a right minus a left. We will still divide the region in case that there are changes in the h, but I think the more important case is how do we compute for this h in a particular example. Let's see. For example, we have this problem we had before. The equation for this parabola is x is equal to 3 minus y squared, which is given by the x coordinate here. And the expression or the equation for this line here is x equal to y plus 1. We'll see that if you want to compute for the height, we now look at the x coordinate of this curve, which is just a 3 minus y squared, minus the x coordinate of this curve, which is a y plus 1, and which will give me a full expression of y. It just remains to show how do we get the limits of y, which is similar to what we did in the previous video where we got the limits of x. Essentially, what we are going to be doing for this whole video is to analyze our region in terms of y, and thus we will be using horizontal rectangles whose heights are right minus left. Let's put that into a definition. If I have two continuous functions u and v of y in the interval cd. Now cd here, please take note, are values of y. So it's the c is the bottommost value for y, and the d is the uppermost value or the greatest value of y. That is part of the region. If in case that v of y is greater than u of y, it means that the curve x is equal to v of y is on the right of the curve x is equal to u of y. Then that means you can compute for the area bounded by the function x equal to u of y on the left, x equal to v of y on the right, to be given by just v of y minus u of I dy c to d. You will see that the form that we have here is very similar as before. The main differences are, number one, the variable that we're using is y, and that means everything is in terms of y. The limits are in y, that means instead of looking on the left and the right, we'll be looking at the bottom and the top. Also, since this is dy, the variable, the height, is the change in the other. So this is y, so this is a change in x. And you will see that the u of y is equal to x, the v of y is equal to x. And we just need to know which is the right one and which is the left one. For us to be able to memorize this well, we will use the same notation as we had before, and that is the area is just h dy. Notice, it's very similar to the one that we had, where CD now is an interval in y, h is still the height, now right minus left, and the dy will be the width or the governing variable that we have. Now, since this is a very important concept for us, I will again be putting that concept on the left side to aid us later on. Now let's have an example. I wish to find the area of the region bounded by x is equal to 3 minus y squared and the line y equal to x minus 1. One thing to note here is that the x is isolated instead of the y. This is a good indicator that we are going to be using the y variable. I will explain more of that later on. Now, similar to what we had before, we need to know the interval CD and the height h here. And for us to do that, we need to first draw the region. This will give us the limits that we will be needing, as well as the orientation, which is on the right and which is on the left. it is good to note that the drawing for this particular region is exactly the drawing that we had before, which is x is equal to 3 minus y squared is a parabola facing to the left, while y equal to x minus 1 is just a line slanting to the right. We need to find CD here, and to find it, we will note that C is the lowest value of y. So a very common mistake here is that because we are so used in using x, we forget that the C and D are values of y. So in this case, when you have decided that you will be using the y variable, look at the bottommost value or the lowest value of y. Unfortunately, I don't know this value here as well as the highest value here. What we're going to be doing is similar to what we did last time, and that is to find the points of intersection. So the points of intersection for this will be y equal to negative 2 and 1. It will be left to all of you to show that this is true. Clearly, negative 2 will be the y value here. It's a little bit lower, and y equal to 1 will be here. So that will give me the interval that I need, which is negative 2 to 1. The height, which is the height of this rectangle here, is computed before, and that is a negative y squared minus y plus 2. And thus, the area will be equal to the negative 2 to 1, and then you have a negative y minus y plus 2 dy. Of course, you can anti-differentiate this, use FTOC to obtain the area 9/2 square units. So this means that the technique that we actually are using is very similar to what we had before. It's just that the orientation is a little bit different. From an x, it now is a y. Instead of looking for the leftmost x, rightmost x, we now look at the bottommost y and topmost y to get the interval. Instead of a top minus bottom in the height, we now have right minus left. But whatever the case is, we need to know what the variable is because there should only be a single variable for each integral. So if I use x, everything is in x, y, everything should be in y. Let's have another example. I want to find the area of the region bounded by the parabolas x equal to 4 minus y squared and x equal to 2 minus y squared over 2. These are two parabolas which are both facing to the left. The graph of these curves is given by this figure. Now it's very important to know which one is which. Of course, in the problem, it is already given, or in the diagram, it is given. However, one good way to know which one is which is by the x-intercept. Clearly, if you zero out y here, the x-intercept is 4, while the x-intercept here is 2. That tells you that this is the x equal to 2 minus y squared over 2. This is the 2. And this is 4, so this is the x equal to 4 minus y squared. If you use vertical rectangles in analyzing this, or that means you will use the variable x, this will be a lot difficult for the reason that you will split this in 3 ways. The first one will be from here to here, this region here. The second is this tip part, and the last one is this bottom part here. So you will be analyzing this in using 3 regions. You can also use symmetry to solve this, but that will be not part of our discussion, so I will skip on that. Anyway, if you're going to use the variable y or horizontal rectangles, you will see that unlike the x that the top and the bottom function always changes, in here the right and the left will never change. The curve on the right will always be the curve on the right, and the curve on the left will always be the curve on the left. Another good indicator that this is this should be analyzed using y is because the functions that we have here have an isolation of x. So it's very easy to solve for x because you don't have a power for x. So let's, without further ado, let's solve for the interval. To find the interval, the interval here, I need the points of intersection, and it will be given by negative 2 and 2. Clearly, this is negative 2, and that is 2. So we are looking for y values. Next, I'll need to know the height. The height here is just the right minus the left. So the area will just be negative 2 to 2. The right function here is just a change in the x. So that means the x value on the right, 4 minus y squared, minus the x on the left, which is a 2 minus y squared over 2. We'll not forget the dy because that's an important part here, saying that we are integrating with respect to y. We can anti-differentiate this, simplify to get the answer of 16 over 3. The best way to master this topic is to do a lot of examples on it. In that way, we'll be able to easily change our orientation, whether we're using vertical or horizontal rectangles. Now, some helpful tips in the conclusion of the area of a plane region. Number 1, we saw that we can analyze each of our regions in terms of x and y. However we analyze it, the answer will be the same. Remember, we are looking for area. So whether I use the vertical or horizontal analysis, it will always have the same area. However, the difficulty will be a little bit different. But what we are sure of is that if you're going to use the variable x, then the rectangle should be a vertical rectangle. And that means if you want to find the area, it should have a dx here. A and b should be limits of x, so that's left to right. And then the height will just be f of x minus g of x. Or, as I have always said here, this is the top minus bottom or up minus down. If you're in y, then the horizontal rectangle is the one that you will be using. In here, you will be using the variable y, and ab here will just be the bottommost y and the uppermost y. And then the height here will be a v of y minus u of y, where the mnemonic right minus left is the one that is being used. It's very important as well to note that the variable should be only one. That's true for limits, the integrand, and the dw, or the variable that we use in this part. Also, the order of getting the things to fill up in your area is very important. You cannot interchange it. For one, the most important one is the variable. It's only by knowing the variable that we will be able to know whether we're going to use up minus down or we're going to use left right in finding the limits. After the variable, you look for the interval. It is at this moment that, since you know what the variable is, you ask yourself if you're going to split. If you're using x, you ask yourself, does the upper function change? Does the lower function change? If you're using y, you ask, is the right function changing or is the left function changing? After splitting it up, you can now find the height h. So though it is very important to find the height, turns out finding the height will actually happen at the last part, after finding the variable and after finding the correct splits and the intervals. And last but not the least, as I've told you before, though the values or the answer, whether you analyze vertically or horizontally, will be the same, the difficulty will not be the same, always the same. If we did not say anything about finding, or we did not say you will use a particular variable or a particular analysis, whether vertical or horizontal, a good way to know which variable to use are the following. Well, the first one is the function. You know that if you're going to use the variable x, you need to isolate y. So if you can isolate y so that you can have f of x and g of x, it means you're going to use x. Most of the time, a complicated x means that the variable should be x. If it is simple, for example, x equal to something, then that means you will use the variable y, because remember, v of y and u of y are functions of y, isolations of x. Another one is the number of splits. Of course, even if the function is very, very easy, if you need to split it around 100 times, it will also not be efficient. To find out which one is more important, it depends on the problem. But this will only come into play if we did not say what type of analysis to use. Otherwise, if you say to use the variable y, please use the variable y. And this ends the topic for area. In the next video, we're going to be talking about arc length and how to find the length of curves using the integral. I hope to see you in our next video. See you!